Hi. Which one of these is on? Hello. So yeah, I'm John. I am an ex-stronomer because I was a former astronomer. I now work for a tech startup here in Austin doing decidedly non-dark matter related things.
Point the mic towards your face.
Who said that? Rachel, you're not as tall as me? Okay. So, this title is, I'll talk to you about what is dark matter. I could just as easily have titled this talk, oh my god, I spent my 20s looking for invisible stuff in space. So this is really just a validation that what I did is not totally off the wall and is actually real. So let's start. Let's start with a working definition for what I mean when I say dark matter. So really just anything that has mass, and mass therefore has gravity, but it's invisible. And when I say invisible, I really mean that, the most invisible thing you could possibly think of. So dark matter doesn't emit light, it doesn't absorb light, it doesn't scatter light. If there were a big cloud of dark matter in this room between you and me, you wouldn't see the dark matter, you wouldn't see a shadow or anything, you would just see me. It would be invisible. So that's what we mean at the beginning of the talk for dark matter. But your spidey senses should be tingling, right? I've told you that there's this stuff that's invisible and it's everywhere in the universe, and you should call me out on that. Right, so there's a principle known as Occam's Razor in science. And how many of you guys have seen Contact? Right, so you've seen this, where she's like, oh, all things being equal, the simplest explanation tends to be the right one. Oh, I had a joke there. And he's like, whoa. This is a really general principle for science in general. When you're evaluating two theories that equally well explain the data, and that's a big if both theories can equally well explain the data, and one of them makes all these weird assumptions about supernatural invisible stuff, and one of them doesn't, you should go with the one that doesn't. So keep that in the back of your mind, and feel free to call me out on that. So the first question I always get is, if dark matter is invisible, how can we find it? And it works like this. Even though dark matter is invisible, it has a measurable effect on things that you can see. So you look for that effect, essentially. If you're looking at a galaxy, the galaxy is made up of stars. The stars all have mass, and they sort of orbit around each other. And you can actually calculate the mass in stars given the speeds of the stars that you measure. So if you add some dark matter to the system, dark matter has mass. That mass produces an extra gravitational force. So the stars that are moving around in this galaxy feel a stronger force, and they have to move a little bit faster. So in general, if you look for dark matter, or in general, anything you can't see, you're looking for stars that are moving way faster than they should be, given the stuff that you actually can see. So we'll come back to this. This is called dynamics, or dynamical modeling, and it's what I did for a living for 6 years. So where did the word dark matter come from? It came from a somewhat famous astronomer, infamous curmudgeon, whose name was Fritz Zwicky. In 1933, he coins the word dark matter in German. But essentially what Zwicky did was he went out and made a bunch of measurements of velocities in a galaxy cluster. Now, a galaxy cluster is a bunch of galaxies sort of orbiting around within a big, giant, dynamically bound object. So all the galaxies are whizzing around in these clusters. And Zwicky goes out and says, oh man, all the speeds of these galaxies are really, really high. And he says, oh, there must be some extra stuff in there that causes the extra gravitational force, that causes them to move a lot faster. And because I can't see it, I'm going to call it dark matter. And that's really what he meant by that. Unfortunately, this was sort of left alone for 30 years, and that makes Fritz sad. Happy Fritz, sad Fritz. Happy, sad. And then until the 1960s, an astronomer named Vera Rubin, who was a remarkable woman. She made a ton of progress and is still an active advocate for women in astronomy. And she's actually really interesting. You should go look her up. But she provided this seminal research that she did for her PhD, went out and measuring the speeds with which stars orbit around the center of a galaxy. And she did this, and this quantity is called a rotation curve. You'll hear me say that a couple times after this. If you go out and you measure the speeds with which stars are rotating, or stars are orbiting around the center of a galaxy, this quantity is known as a rotation curve. And the techniques you use, we still use today. It's called spectroscopy. It involves splitting the light that comes in from the stars that are in your object, or the gas that's in your object, into its component wavelengths. And stars that are moving faster towards you have their wavelength shifted towards the blue, and stars are moving away from you have their wavelength shifting to the red. So if you make a measurement of the wavelength of light as you go out into the later parts of the galaxy, you really have a measurement of speed. So that resulting thing is called a rotation curve. Now, what everybody expected to find was this little red plot here, where the farther you are from the center of the galaxy, where all the mass is, presumably, the slower the stars are going to be moving around the center. It's the same thing as the way this works in our solar system, right? Pluto is the farthest from the sun, or Neptune if you believe other people, which I do. So Pluto is the farthest cool object from the sun, and its speed is a lot slower than Mercury's, just because the force of gravity is so much weaker all the way out there, right? So that makes sense. If all the mass is concentrated in the sun, things that are farther away from the sun will move slower. So scale this principle up to galaxies. Stars that are farther away from the big galaxy in the middle should be moving slowly. So that's what they thought they would find, this red curve. Instead, Vera Rubin's sample, she found every spiral galaxy she looked at had this sort of something that looks like a cartoon of this white line over here, which is remarkable. The farther you are from the center of the galaxy, which is presumably where all the mass is, the stars are still moving just as fast. So the conclusion that she came to, and the conclusion that most astronomers accept, is that there must be extra stuff in there causing a stronger gravitational field, causing those stars to move faster than they otherwise would be. And this extra stuff is called dark matter. So this is sort of the first time when dark matter enters the standard canon of what's out there in the universe. It's stuff that extra mass that we can't see that's keeping rotation curves in galaxies flat. So a quick aside, to justify my own existence, you can also do this technique not just on spiral galaxies, where it's a little bit easier because the stars are all going in circles and you can kind of make a bunch of assumptions about that. The kind of galaxies I worked in, you can't even see them out here with the projector, but this little smudge in the left is a dwarf galaxy that's really close to the Milky Way. And it's really, really small, but it has a ton of dark matter in it. So they're really interesting objects. And back in the day, I took some data from the 107-inch telescope at McDonald Observatory, blah, 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 made some plots. Essentially, I was just measuring the velocities of stars in this galaxy. And that all goes into a model that's super duper fancy and produces a bunch of squiggles that you don't have to worry about. But what this was is not just detecting the presence of dark matter, but detecting where it's distributed in the galaxy. So is it more centrally concentrated? Is there a lot more dark matter in the center than we thought? Does it sort of spread out the further you go outside the galaxy? This is what I worked on. And talk to me afterwards. I'd be super stoked to talk about it with someone. I tell people that's the reason I left astronomy, is because there were 7 people in the universe that thought my work was interesting. So, all right, let's go back to our definition for what is dark matter. The new, better definition, and this is what most astronomers believe today, this is the consensus, is that dark matter is some sort of new, as of yet undiscovered type of particle that does not interact with normal matter in the usual ways. And what do I mean by that? So normal matter, normal matter is things like protons, neutrons, electrons, and whatever they make up. So everything on the periodic table, you and me, even stars, gas in other galaxies, this is all normal matter. And normal matter is constrained, it has a few ways in which normal matter can interact with itself. So you may have heard this before, but we believe there are 4 forces that are available in the universe for which matter to interact through. There's the force of gravity. Anything that has mass exerts a gravitational force. There's the electromagnetic force, which is the reason why I'm not falling through this floor, because the electrons in my boot are pushing on the electrons in the top of the floor, and otherwise that'd be kind of icky. Then there are 2 forces you're probably less familiar with. There's the strong and the weak nuclear forces. These are really only important when you're on really, really small length scales, like inside the nucleus of an atom. These become important. But the ones you're probably most familiar with are the top 2. So this dark matter particle that we believe exists just does not interact with those with the electromagnetic or the strong force. It interacts primarily through gravity, and then a tiny bit through this really, really weak force over here. So the name we give for particles like this is weakly interacting massive particles, and because astronomers love their acronyms, that of course becomes a WIMP. So let's get to the important part. Why should you believe me? So I just told you that dark matter is this new thing that no one's ever seen and that you can't touch. And this is the evidence right here. This is the strongest evidence we have that I know of that dark matter is indeed a new type of particle that does not interact with itself or with anything else. So what this is an object, it's called the bullet cluster. It's actually 2 galaxy clusters. So you see one on the right, or one on the left has gone through the one on the right. And a galaxy cluster, again, is just a group of galaxies. It also has a bunch of hot gas. And if you shine an X-ray telescope at a galaxy cluster, you'll see all this hot gas emitting X-rays, and that's how you know it's there. And then the dark matter, each galaxy cluster has its own dark matter halo associated with it. You can't see the dark matter directly, but you can detect it using a technique known as strong gravitational lensing, which I don't have time to get into here, but it's a really good way to make a map of the dark matter distribution here. So the really critical thing here is these clusters, one went through the other one. The galaxies are sort of passed next to each other. They don't really care. The gas is located right in the middle of the system. And you can see it's clearly shocked. It's like it's interacted with itself. There's a bit of a wake on the smaller galaxy cluster, like you would have a boat trailing a wake. And this only happens if the gas can interact with the electromagnetic force, if it can like slam into itself and shock and heat up. And now the really key is that the dark matter, the blue stuff, is not like that. It's not distributed like that. It's just in the center of the galaxy cluster, and the implication is that it just sort of passed right through itself. So people can give you alternate theories for dark matter, and I have never seen one that explains that in a satisfying way. But let's try. This is a useful thought experiment. Let's go back to trying to explain the observation that galaxy rotation curves are flat. So rather than introduce this new mysterious substance, how else can we make a galaxy rotation curve be flat without adding extra mass? Hint, the rotation curves are based because we sort of know how to extrapolate, turn gravity into mass into speed, and this is all happening with our laws of physics. Well, our laws of physics could be wrong. So there's this theory out there known as the modification of Newtonian dynamics. It's called MOND. And it actually has a clever idea that maybe Newton's laws of motion are wrong. Newton's laws of motion are wrong sometimes. And we actually know that Newton's laws of motion break down. They break down around really strong gravitational fields around black holes. But maybe they also break down around really, really weak gravitational fields. So like way out in the edges of the galaxy over here, maybe the acceleration's so low, and we've never experienced anything like that, so we have no way to measure that. So this is actually a pretty cool idea. Let's go back to Occam's Razor. Which of these two explanations is simpler? There's a bunch of magical stuff that you can't see, that you've never known of before, or we're wrong, which we've been before. So MOND is actually a really attractive theory, but wait, I'm going to flip it on itself. So this is how you would calculate a quantity known as the action in general relativity, and it's like a beautiful theory. Look at this equation. It's like you can write it in one little slide, and this is the same quantity in MOND. There's like a hyperbolic sign in there somewhere, all kinds of nasty coordinate transformations. There's a 32 down there in the bottom. When have you ever seen a theory be right with a 32 in it, right? Like, it's not F equals 32 MA. So I don't want to live in a world where that's the correct explanation of nature. I think, and the Occam's Razor argument is that the simpler explanation is probably the most likely. So this is why MOND is stupid. But, so this is an argument against it. It's not direct proof, but this is direct proof. It just doesn't work. It works really well. It's a really cool solution to get flat rotation curves. But if you apply the same laws that they say, like this is the new version of Newton's laws, you apply that, and it doesn't get the speeds right in galaxy clusters. So why would nature be different, why would the force of gravity be different in our regime and in galaxy rotation curves and in galaxy clusters in yet a different way? That just adds complexity. And now the simplest explanation is, yeah, there actually is some stuff out there that we can't see that is consisting of dark matter. So, okay, that, by the way, that doesn't stop the Mond people from, every time you give a talk, they're like, what about Mond? And you're like, that's stupid. So I have like this rehearsed thing that I always give at the first Mond question, but, so yeah, let's throw that one out. But let's think of a less exotic explanation for dark matter than some new particle we haven't seen yet. Okay, so again, all we're trying to do is trying to get a galaxy rotation curve to be flat. Can you think of another way it can do that without adding a WIMP? So let's add some extra mass. Can you think of anything that would be kind of hard to see, has mass, something black and hole-shaped? Yeah, right? I heard it. So if instead of dark matter particles, dark matter was just a bunch of black holes out at the edges of the galaxy, that could work. Of course, there's no theory for why that configuration would exist. Nobody can explain that. But it could also be things like old really dim white dwarfs and neutron stars, which are sort of the embers left over when a massive star or massive or low mass star burns out. Those are really hard to see. And if there were a bunch of white dwarfs and neutron stars out in the galaxy on the other side at 100,000 light years, you'd never see them. So that's plausible. Add to this your list of stuff that's in space that doesn't shine, brown dwarfs, planets, space junk, aliens. So collectively, these things have a name, and because they're the counter theory to WIMPs, they're called machos. Massive compact halo, and that acronym is a bit of a stretch, but it has to be machos, right? So this is the theory that people put forward. This is, okay, maybe dark matter is not a new fancy kind of particle. Maybe it's just this sort of like routine astronomy stuff that we already know exists. Maybe it's just that's out there in space. So that's a theory that we can test. And one of the tests was done. It uses a process known as gravitational microlensing. And so if you've heard of gravitational lensing, it's what happens when a massive body distorts the space-time around it. So light that travels near that massive body gets its path bent through space-time. So imagine we're looking at a distant star, and between me and the star, a macho happens to pass. And you can't see the macho, but the macho bends the space-time around itself, and the light from that star has to travel the bent path. So the net effect here is that the star that you're looking at appears to get brighter and then go back down in a period of about 30 days or so. So that happens. There were 2 surveys that I know of that were done that tested this hypothesis, and they looked at a bunch of stars, distant stars in the Milky Way, and they observed like a lot of these macho events. So these are found, but the cool thing is you can do the math and say, okay, I detected this number of events. How many machos does that infer? And that number is so much lower than the number we need to add mass to the rotation curve of the Milky Way to get it to be flat. So we're still missing a lot of matter. So this theory is sort of by the wayside as well. So it really is remarkable. Dark matter really is the simplest explanation to this hypothesis. It's this, think about how crazy that is. I just told you that there's the stuff that you can't see, smell, taste, hear, touch, infer in any way other than its effective gravity, and yet it's everywhere in the universe, right? And I've only given you 3 or so arguments for it. I think Mike is going to give you another couple arguments for it, and there's a bunch more after that. So the last thing I want to do is have everybody hold your hand up like this. Don't be shy. So count to 1. Ready? 1 Mississippi. All right. 10 million WIMPs just passed through your hand in that second. All right. And that's heavy shit.
All right, we've got time for some questions for the ex-astronomer, the sellout here, right up front.
I'm very interested in you mentioned in the white dwarfs. Approximately 1% of all the stars in a given galaxy are decaying white dwarfs.
Oh, I should know that. So the question was, what percentage of the stars in a galaxy are white dwarfs? Do you know? It's a number that people know. So we're really good at... I don't do this for a living anymore, so comparable to the total number of stars, says the Craig Wheeler in the crowd. And the reason we know that is we know a gas cloud turns into X number of massive stars and turns into Y number of low mass stars. And this is really, really well tested and measured, which is part of the reason why it's impossible for a bunch of white dwarfs to just be out in the middle of the galaxy somewhere by themselves. It's a good question.
Let's go right up front here.
You mentioned when you were doing microlensing that the star looks white. Why don't you get a double image?
So the question is, when you look at microlensing of a star, why is the star just brighter instead of being double imaged? Like you may be more familiar with these when you talk about distant galaxies and strong lensing. So I think the answer is that the star is unresolved. And so rather than get another image, you just get a brighter image of the star itself. So what's happening is that more rays of light from that star are being bent into your path than otherwise would be.
All right, anybody upstairs? Let's look straight back upstairs. Or is that just a camera? Okay, that was just a camera. All right, down here then.
See that the position of the star change as the light star passes the gravitational.
That's correct. So the comment is that when Einstein's general theory of relativity was being validated by I believe it was Eddington and others, the measurement they used to confirm this was they went out and looked at stars that were really close to the sun, and those stars actually so you can't do that when the sun's up. And the sun's always up when you're looking at it, except when there's an eclipse, right? So if the moon happens to block out the light from the sun, you can see stars that are really angularly close to the sun. And when that was observed, their light was observed to deflect inward or outward. I don't know which, probably inward. So that was what proved general relativity. So the question is, why does that not happen in these microlensing events? And I think the answer is because the sun is this big disk that's really close to us, and the macho is this small compact thing that's really far from us, and the geometry is just off.
All right, one more question. Let's see here. On the side here.
Why do we think that dark matter interacts with the weak force?
I'm going to leave that to the next speaker. I think he's going to talk about that.
All right, that was
if
a
he
good
doesn't, come
cop-out
find me.
question. All right, one more. Straight back here. He had his hand up early.
Yeah, the rotation curve. It's the same calculated and measured out to 10,000 light years. Is the black hole at the center of that galaxy clearing out the WIMPs?
So the question is about the rotation curve being flat out at large radii, and the question is, does the black hole influence that at all? And the answer is absolutely not. The mass of the actual galaxy, so there's two reasons why it wouldn't. The mass of the black hole is, so most galaxies have a 100 million or so solar mass black hole at the middle of them. And that seems really massive, but the mass of the galaxy disk itself is like in the many billions and hundreds of billions of solar masses. So the dynamical gravity effect of the black hole is negligible out there. The other question is the black hole, so black holes, when you dump matter on them, they tend to emit radiation, really hot radiation. It's one of the coolest ways to make energy. So the question is that black hole, if it turned on in one of these episodic accretion events, did that clear out the WIMPs from the inner portion of the galaxy? And the answer is no, because we believe that WIMPs only interact with that weak force. And the energy coming out from the black hole would be in photons, electromagnetic force carrier particles, or it would be particles themselves, which would, either way, that would require the electromagnetic force to do something. So it's not the wind doing anything, and the point of the rotation curve being flat is that there's just stuff out there, and that stuff necessitates an extra gravity.
All right, let's thank Ex-stronomer one more time.